Everyone is ready? So we're now going to talk about multi-criteria decision models. Okay. Oh, no, we had to show all that Excel thing, nah? I see. Okay, we'll do that first then. Okay, so let's. Oh, sorry. Yeah, thank you. Okay, so let's do the Excel related one first. I think the assignments I've given have been one or two are from this chapter itself. So let me do the LP version of that. Okay, so I'll take the textbook and solve some problems from the textbook. Whatever, anyhow, really. Right, so assignment and transportation problems through Excel, right? Where are we? Distribution network. Okay, so here we are. We'll increase the, yeah, all right. Oh, so here are some problems. Okay, so yes, let's do this one here, all right? So Premier Consulting, two consultants, Avery and Baker, can be scheduled to work for clients up to a maximum of 160 hours over the next 4 weeks. A third consultant, Campbell, has some administrative assignments already planned, is available for clients up to 140 hours for the next 4 weeks. The company has 4 clients with projects in progress. Estimated hourly requirements are client A 180, client B 75, client C 100, and client D 85. So these are the demand and those are the supply, right? Supply is 160, 160 and 140 here, 160, 160 and 140. Okay, so the hourly rates vary for the client, consultant-client combinations, including project type and consultant experience. Rates in dollars per hour for each combination are given below. Okay. Developer network. So we want to formulate a linear programming problem with optimal solution, providing the hours each consultant should be scheduled for each client to maximize the consulting firm's billings. So it's a maximization problem this time. Okay. All right. Now let me see if I can copy this. Okay, I can copy it without the D, of course, but okay. Anyhow, now let me put this in Excel over here. Okay, so let's see. Oh, all right. When we get something like this, what we have to do? So basically, what it's done is it's taken this all into one. All right, we can separate it by using text to columns here. Okay, so go to text to columns, and basically everything is with a space in between. So if you put space, it will all come out fine. Okay, right? So it's come out fine. It looks bad, but it wasn't so bad. Okay, so these are the costs. Sorry, the not costs, rates. Yes, these are the rates. And we can have the supply and demand. Okay, so supply and demand. And demand here. Now, what was the demand? What was the demand? 180 something something, no? 180, 75, 185. Okay, 180, 75, 180, 75, 100 and 85, right? Yeah, I think that was it. Yeah, okay. And what is the supply? Well, each of these is 160 and this person is 140. 160, 160 and 140. Okay, so notice that we have excess supply, correct? Excess supply, okay? So to solve this, I'm going to make a copy of this over here and eliminate all these numbers. These now become the variables, These are my variables. Okay, so how much to, how many hours to bill this for. And now, the total hours that every works is the row sum here. The total hours that each of the agents or consultants work is the row sum here. And the total hours given to each client is the column sum. Right? Column sum here. And the total profit on the total billable hours, or total bill we'll call it, is the sum product of the whole thing. Rate multiplied by number of hours worked. That's how. Okay? And very simple. Okay, so now we can, it's already actually. So take solver. We want to maximize the total billed hours, right? We want to maximize this total bill or total revenue basically. What are the variables? These, which ones are the variables? These are the variables and constraints. Now, okay, now because demand constraints are less, so these should equal to the demand. We want to satisfy all the demand. On the other hand, supply constraints, because we have excess supply, supply constraints will be this less than equal to the supply available. Okay, very, very simple. And we solve. Okay, so what are we saying? Well, Avery is sent for 40 hours to B, 100 hours to C, Baker 40 hours to A, 35 hours to B, 85 hours to D, and Campbell 140 hours to A. Right? And that meets all the requirements. And we can see that Avery has 20 hours extra. Okay. Now, suppose it was balanced. Okay. So suppose it's balanced. Let's make it 150, 150. Huh? Okay. Why discriminate? Make it 150, 150. So when we have a balanced problem, okay, when we have a balanced problem, both supply and demand constraints we take as equal to. So change this to equal to now. Right? And we can solve. Okay, so now the configuration is slightly different. Yeah, slightly different. Okay, so when it's balanced, make both equality constraint. When it's unbalanced, whatever is excess has more. So for example, suppose there was much more demand. So suppose this is 150, 100 and maybe 160, 130. Okay. Clearly the demand is in excess now, right? And so we won't be able to meet all the client requirements. So what do? Well, we change the demand constraints into less than equal to. What is this? This is demand constraint, right? You can see it really. D50, yes. Okay, so we change that to less than equal to. And now when we solve it, we'll get a solution, but notice not all clients' needs will be met. Only the ones that are economical will be met, or more profitable in this case. Okay? All right, shall we try an assignment problem? Oh, by the way, also notice one thing about the sensitivity report. So, negative, yes. Now, then reduced costs are negative because we're maximizing the profit. And so, for example, if we assign Avery to D, we're losing $10 of profit. If we assign this one, Campbell to D, we lose $25 in profit. So it's like an opportunity cost. Okay. And in both these cases, the shadow prices are positive. Okay, so excess supply will not help here. All right. Okay. All right. Anyway. No. Here, this is the first one. Excess supply. This is excess supply. 160, 160, 140. So this isn't the problem. There should have been some negative supply. I see. Okay. All right. Maybe when we do with equality. Okay. Anyway, let's do another one. Or shall we do this by hand also and see? Okay. So we'll do this by hand also. So how to do by hand? Okay. So let's do by hand and see. Okay. We'll come back to this. Here. Okay, so we'll make one big table. All right, so here's a table. What is it? 4 clients, right? So, all right. Okay. Okay. Oh, that's okay. We can move this. Okay, and last one is here. Okay, so now we'll put in the. Okay, these are profits. All right. So what are the profits? 100. Okay. Now, one simple way when we have a maximization problem, one simple way to convert it into a minimization problem is to take the largest profit and subtract everything else, so that it becomes like opportunity cost. So here the largest profit is this one, 155. So we'll take 155 minus everything else. Okay, so that will become 55, 30, 40, and 55, right? First row is, so 55, 30, 40, and 55, right? Okay. Next one is 55 minus this, right? 55 is 35, 20, 40, and 35. 35, 25, 35, 20, 35, 20, 40, 35, 20, 40, and 35. Was it 20 or sorry, yeah. What is this? This is not, I think, at all. Oh, you did this one. Yeah. No. 35, 20, 40. Yeah. Okay, next. 0, 5, 15, and 25. 0, 5, 15, and 25. 0, 5, 15, and 25. Yes? Okay, now supply and demand. First one is 180, 75, 100, and 85. So 180, 75, 100, and 85. Now, one other problem is that because the initial problem was not balanced, right? Initially, we had 160 plus 160, 320 plus how much? 320 plus 140. That's 460. Huh? 460, and the demand totally is how much? 300 something. No. How much? 2, 360, 360, 430. 430, which is 30 less, huh? No, 20 less. 440, I think, yeah. Okay, so because of that, when we try to solve this by hand, we need to introduce something called a dummy row or the dummy column. So one more demand point we'll have to introduce here with costs equal to 0. Okay, costs equal to 0. And the excess supply comes as the demand there. The excess supply is 20, and now this is balanced. 160, 160, and 140. Okay, this is a dummy column. Right? So the excess supply has been put here, and the costs are all equal to 0. So when we're trying to allocate now, we'll try to allocate, of course, in low cost cells first. So let's try to allocate here first. These will wait for the end. Okay. So how much can we allocate here in this cell? So 140 is available, 180 required. So 140 will allocate here. Yes. May not have been a good idea, but okay. Anyway, we'll see. All right. So this one is completed, and 40 units remain here. Right. Yeah, low cost cells. So there are zeros here, but this is an excess. So we'll put the 20 here at the end. That we'll do later. Okay. So since we have to allocate, and since we know that the excess is there, we've seen the solution already. We'll put the 20 here just to save some time. Actually, we'll put the 20 here. Okay. So this is complete, and 140 units are left here. Okay, so now we can't allocate in any of these. Okay, so these are all done, and this row is also done. So out of these, where do you want to allocate? So we allocate here 20, these to them. Yeah, so 75 here. We'll allocate here. All right, 75 and 95 remain here. Now, 85. Yeah. 85, right? 85 plus 75 is 160. Yes, 85. Okay, so okay, all right. So what can we do next? So this column is also anyway. That column is also. All right. Let's try allocating in these 35s next. So let's put a 40 here. Okay, 40 here. So this 40 is over. 85 minus 40 is 45 here. Okay. All right. It shouldn't make any difference. So we'll put 100 here. Okay. So 40 remains here. And now we can put 40 here and 45 here. Okay, so this is our initial basic feasible solution. So initial. So now remember we calculate UIs and VJs, right? So U1 equals 0 for this row. Now these two are empty cells, so we start here. V3 equals 40. V4 equals 55. And V5 equals 0. Okay, so this row is completed. Now if you come here, U2 equals how much? U2 is 35 minus 55, which is minus 20. Okay. And now we can calculate these, right? So V1 equals 35 minus 30 is minus 20 is 55, and V2 equals 20 minus 20 is 40, and U3 rather is minus 55. Okay, U3 is minus 55. Okay, so let's see what we get. So let's put it in blue this time. So delta ij here is 55 minus 0 minus 55, which is 0. This one is negative, right? Everyone can see 30 minus 0 minus 40 is minus 10. Minus 10. Here 5 minus minus 55 is 60 minus 40 is 20. So that's plus 20. No problem. 40 minus minus 20 minus 40 is plus 20. So again, no problem here. Plus 20. 15 minus minus 55 is 70. 70 minus 40 is 30. So again, no problem here. 0 minus minus 20 minus 0 is plus 20. This is plus 55. Okay, so no problems here at all. Now this one, 25 minus minus 55 plus 55 is 25 itself. So no problems in these. So the real worry is this one. Okay, and the chain for this is this cell with these 4 cells here. So this cell, this. Okay, so plus theta here. So plus theta if I sign here, I'll have to do minus theta here, plus theta here, and minus theta here. And if I look at the minus theta cells, theta has to be equal to 40. Okay, so theta equals 40. Okay, so again I have to create this table here. I think it's a bit smaller, but anyhow. Okay, anyway, these are 2 zeros. Oh, that's okay. All right, so now the numbers. So 55. Okay, 30, 40, 55, and 0. What is this? 55, huh? 55, 20, 40, 20, 40, 35, and 0. And 0, 5, 15, 25, and 0. Okay. Now, theta is 40. So, 40 units will come here. Okay. 100 remains unchanged. Okay. This becomes empty, and this remains unchanged. Okay, so 40 has moved there. This remains unchanged, 40. This is 140, remains unchanged. This becomes 35. Okay. This becomes 85. And okay, so U1 equals 0, V2 equals 30, V3 equals 40, and V5 equals 0. Okay, now here U2 equals, okay, 30 minus 20 is 10. So now V1 equals 55 minus 10 is 45, and U3 equals minus 45. And here V3 equals, V4, sorry, equals 35 minus 10, which is 25. Okay, and now let's calculate these. 55 minus 0 minus 45 is 10. Oh. U2 equals 10. Yeah, okay, all right. So, the first row we did U1 equals 0. Right? So, from which we got V2 equals 30 and V3 equals 40. Right? Now, when we want U2, we have to go to this cell here. So, U2 plus V2 equals 20. And since V2 equals 10, oh, it's minus 10. Huh? Oh, minus 10, right. I'm sorry, U2 equals minus 10. 20 minus 30 is minus 10 here. Yeah, thank you. And V2 must be 35 minus 10, which is 45. Yeah. It was earlier minus 20, now it's minus 10. Okay. Yeah, thank you. Okay. Oh, even this will change. This will become 65, is it? Oh, 65, huh? 55 minus 10 is 65, right? Okay, 65. And this will become minus 65. Okay? So, alright, so this becomes minus 10 now. Okay? So, that changes everything. This one is positive, so plus 10. I'll just write plus since it's positive. This one is also positive. 10 minus 40 minus 10 plus minus 40 is positive. We're only worried about negative things, right? 0 minus 10 minus 0 is plus 10, so positive. This is also clearly positive. 25 minus some 65 and minus 45 clearly again will be positive. 15 and that also will be positive. No problem about that. And finally, 5 minus 65 is 70 minus 30 is positive also. Okay, so these are not the issue. The issue is here. And our cycle, what do you call it? Our cycle is here, right? So not cycle, chain. So plus theta will apply here, minus theta, adjust with plus theta here, and minus theta here. And in this case, both of them are equal to 40. So theta has to be 40. Okay, so this will hopefully be our last table for this problem anyway. Okay, so theta equals 40. Oh, okay, let's push this aside. Okay, can edit. Oh, sorry. Okay, anyway. All right, so. Okay, so now this will get how much? 40. This is 40. Okay. Now I'll do the other ones first. Okay, 40 plus 35 is 75. Yeah, 75 here. This is 140, not changed. This is 100, again not changed. This is 85, again not changed. And this is 20, okay? Now, the problem is when we're dealing with this. Now, you'll notice both of them are 40, so both become empty. But then there's a problem. We cannot make both equal to, we cannot make both empty because we must have m plus n minus 1 basic cells. So we must have that, right? So here we need 3 plus 5 minus 1, so 7 basic cells, and these are 6. So one of these has to remain basic. To do that, we put an epsilon here, okay? So I'll write it as epsilon. What that means is it's 0, but we're considering that cell as basic, right? This is called a degenerate solution. When we have this type of problem, happening, that an empty cell, a cell that has no allocation, has to be considered as basic. We call that a degenerate solution. We cannot keep it 0 because we cannot keep it empty because we must have m plus n minus 1 allocations to calculate the ui's and vj's. And so we put an epsilon. Epsilon means 0, but we're considering that as a basic cell. Okay, and the rest is as usual. Okay, so this is 55, this is 30, 40, 55 again, 0. Zeros are easy to draw, so draw them first. And 35 here, 25 here, 40 here, 15 here, 5, 20, 55, right? 55 and 0. Okay. All right. So again, take u1 equals 0. Okay, in the first row. So v1 equals 55. That was straightforward. Right? Then v2 equals 30. v3 equals 40. And v5 equals 0. Okay, so that's from the first row. Now in the second column, we can go here. u2 equals how much? 20 minus 30 is minus 10, just as before. Okay, and now I can find v4. v4 is 35 minus 10, which is 45. And in the first column, I can take this and write u3 equals 0 minus 55, so minus 55. Okay, and now I can calculate all these. So 55 minus 10 is 65, minus 55 is plus 10. I think it's optimal now. Here this is 5, minus 55 is 60, minus 30 is plus 30. This is 40. 40 minus 10 is 50. Minus 40 is plus 10. Here 15. 15 minus 55 is 70. 70 minus 40 is plus 30. 55 minus 0 minus 45 is plus 10. 0 minus 10 minus 0 is plus 10. 25 minus 55 is 80, minus 45 is 35, plus 35. And finally, 0 minus 55 minus 0 is plus 55. And so all cells have positive delta Ij, so it's optimal. Okay, and we can work out the total cost. Only difference is epsilon is 0, so it will be 40 into 55, 100 into 40. This is also 0. 75 into 20, 85 into 35, 40 into 0. Oh, acha, we have to go back and write it in terms of profit. Sorry. So okay, so we need to write everything in terms of profit. So where was it? So we're allocating 40 into 100. Okay, 40 into 100 is 4,000, right? So 4,000 there in terms of total profit. Then 100 into, oh sorry, not that one. 100 into 115. So 100 into 115 is 11500, right? 11500 comes there. 40 into 100, yes. Okay, 100 into 115, okay. Next is 75 into 135. Oh, 75 into 135 is, oh, I've seen a calculator outside. I'll just bring it 1 second. I'm struggling so much. Okay. Luckily, someone has left their calculator for us, so. Okay, so it'll be easier now. Right, so 40 into 100 plus 100 into 115 plus 75 into 75 into what? 75 into 135 plus 85 into 120 plus 140 into 155, right? And so that gives us 57525. So 57525 is the optimal profit. Okay, optimal profit is, or revenue, that's not profit. Optimal revenue is 57525. Okay, quite straightforward. I think we got that first time also, right? This is a different one. Okay, we can do it again. 160, 160. It's the same one, no? Oh, we changed these, no? Oh, sorry. 160 here. 160, 160. And this was 180, 75, 185, right? Okay, so, all right, just maximize again. No feasible solution because it's equality. This should be equal to, okay, and this should be less than equal to. And now we'll solve, right? 575, 925, huh? Oh. 4035, huh? Did I miss out something? This is this one. But it wasn't optimal, huh? This is this one, right? 185. Then we must have made a mistake here, no? Okay, let's see. 30, 40, 0, 40, we have 30 here. So minus 10. So 65 here, so it's minus 10 only. 65. That's strange. Very strange. Uh, 55. Oh, I think I see what that, I see. Oh, I see what the problem. This was a 35 which you wrote as 55. That was a mistake. That's why that became, yeah, so that's why it moved from there to there. We wrote this, we wrote as 35, and then next one we wrote as 55. That's right. Okay, my mistake. I'm sorry. Yeah, bad handwriting is the problem actually. Okay, so that's the problem. So actually this turns out to be the optimal solution because actually this is 35. So if this is 35 here, then what happens is this becomes 35 minus 10 is 45, right? And then this becomes plus 10, and so it's optimal. The rest of them don't depend on this. Okay, so that's why. Okay, anyway, that was. So let's try to solve an assignment problem also using this. Okay, distributor orders. Okay. Distribution cost. Okay. Demand and supply. Supply is. Okay, this is similar. Okay. All right. So shall we try this one? Yeah. So this is a power generation, supplies electrical power to consumption. One of the problems in the assignment is similar, not exactly, well, it's a little more confusing than this. So this is a nice one to do. Okay, main power generation plants are located in Los Angeles, Tulsa, Seattle, and following table shows the demand, various things. Okay, so, all right, so, modify text. Okay, thank you. All right, so let's go to this and paste it here. Okay, it's worked a little, but okay. All right, so this is Los Angeles. And then we can forget these two. Delete left. Okay, so Tulsa, and this is demand. And we don't need these. Okay. All right, this is SF we'll put, and then delete this one. And this is Park. Don't need to put. Okay, so these are the demands. This is the cost. Cost, and so on. Oh, it's not a number. Okay, so we have to change it into a number now. How do we get rid of the dollar sign? Okay, we have to edit each one of them. Convert format, will that work? I doubt. Okay, let's try. It will be a string format. That's the problem. Yeah. If you try to convert to number, let's see what happens. It's not taking, see. The problem is it's not thinking of it as a number. It thinks that it's some characters type thing. Select all cells. Okay, I can do that. All right, so go there. Okay, if I try to put number, see, it's not working. It's taken that as a character. It's not even in currency format. If it was currency format, we could then convert. But because it's not currency format, it's not allowing. See, if it was in currency format, if you added a 1, it would take it, because at least currency is a type of number, no? Because that's why I tested by adding 1. That's always how to test what format you're dealing with. Because it didn't recognize that as a number at all, it's not thinking of numbers here. Excel is a highly thinking machine. Anyway, it's almost done, so no problem. I hope I don't delete any of the numbers actually. More serious. Okay. So, what are we told? So, we're told that these are the costs. The cost to supply electricity is this much, and the demand is this much. So, we have to minimize the total cost. So, how much supply? How much to be supplied from each of these to each of these? Okay. So, I'll copy this whole thing over here. Okay. Anyhow, and remove these. Okay, so these are my variables now. Okay, and as usual, I'll take row sums and column sums. Okay, that's this. And of course, we'll make it look like a real variable itself. Right, yeah. Okay, and okay, let's for a change write the total cost here. It's the sum product of all of these with all of these. Okay, that's my objective. Okay. All right. Now, the first part of the question that they've given us is, so if there are no restrictions on the amount of power that can be supplied by any of the power plants, what is the optimal solution? No restriction means, well, we can put any number, so there's no restriction on supply, right? So what we can do is we can choose a large number, larger than any of the, well, or we can take the total demand and put it in one of those. So, of course, we can calculate the total demand. Total demand is how much? 10925, right? So anything larger than that, we can assign there. Okay, so no limit on that. So let's take 12,000. Okay, so 12,000, I'm putting a supply for all of these. Oh, what happened? Why did it come like that? Oh, 12,000. Huh? What's that? What's that formatting? All right, so 12,000, 12,000, 12,000. Okay, so let's take that first and let's solve it. So solve. We're minimizing the total cost this time. Where are the variables? The variables are here. Variables are here. And usual set of constraints. So demand constraints are equal to, in this case, demand is rows, and supply constraints are less than or equal to excess supply. Okay, so what will happen? Okay, so a peculiar type of thing. Seattle is entirely, Seattle. Is that right? Yeah, okay, Seattle. Okay, that's an obvious one, of course. Okay, so Seattle, Portland. Okay, so from Los Angeles, San Francisco, Reno, Laramie, or whatever park, Flagstaff. These are the ones that are serviceable. From Tulsa, this Durango or whatever it is, and from Seattle, Portland, Boise, and Bozeman or whatever. So individual type of things. But of course, that's not the end of the story. They want us to also put in some specific things. So let's change that now to what they want. So what do they want actually? So they said a maximum of 4,000. Okay, 4,000 means 3 times 4,000 is 12,000. Okay, so maximum of 4,000. Okay, so let's put 4,000 here. So 4,000, 4,000, and 4,000. Okay, so now the same thing with proper constraints. Okay, again minimize. These again are the variables. Again, demand is equal to this demand here, and supply is less than or equal to available supply there. Okay, and solve. Very easy, right? Okay, so now things get a little mixed up. Okay, because earlier we had unlimited quantity, now it's limited. So we're not using most of Tulsa, only about little more than 50%, right? 58% or something. Okay, so very simple one. Okay, so let's try a assignment problem now. Enough of these. Yes. Oh, this is not assignment. This is still not assignment problems. Okay. Shipping costs. No assignment problems. Right? Where did the assignment problems go? Cost per gallon. Here they are. Okay, so all right, let's do this one. Okay, so what does it say? Carpet Plus sells and installs floor covering for commercial buildings. Brad Sweeney, a Carpet Plus account executive, was awarded the contract for 5 jobs. That was 1 to 5. And because of the commission, Brad will earn depends on the profit Carpet Plus makes. Brad would like to determine an maximization assignment that will minimize the total installation costs. Currently, 5 installation crews are available: red, white, blue, green, and brown. And the following table is the cost here. So we want to minimize the cost of assignment. Okay, minimize the total cost of assignment. So the usual. Right? What do? We'll copy this over here. Okay, it has happily done it for us. Okay, so these are the costs. Very nice. And we'll copy this again over here and remove all this. And again, make it all into smaller squares. Okay, and again, row sums and column sums. So everything is in terms of row sums and column sums. And finally, the total cost. Total cost is, again, sum product. Okay, and we're ready. So, what do? Well, we're minimizing the total costs. These are the variables, all of the variables. And what are the constraints? Well, because this is balanced, number of jobs and number of agents are the same, everything must be equal to 1. So this must be equal to 1, just type a 1 here. And these must be also equal to 1. Okay? And we're done. Okay. So, alright, so red team goes to job 3. White team goes to job 5, blue team to job 4, green team to job 1, and brown team to job 2. Okay, so, alright, shall we do it directly? Let's also solve it. Hungarian assignment method. Okay, so, okay, let me save this one. Though it's wrong, we'll save it anyhow. It's right for a different problem. It's called Modi method, right? Okay, so just imagine this to be 55 also, and then it's correct. Oh, I closed it. Okay, anyway. So, what do we have? So first let's draw a box. Let's see. Okay, there's a better box. Huh? Okay, so since these are costs, directly we can do row reduction. So in the first row, 30 is the least, so this becomes 0, 14, 8, 17, and 1. Right? 0, 14, 8, 17, and 1. So 0, 14, 8, 17, and 1. Okay? Next row, 25 is least. So 0, 7, 20, 19, and 0. 0, 7, 20, 19, and 0. 0, 7, 20, 19, and 0. Okay. Next one, 23. Yeah? So 0, 17, 14, 0, 17, 14, 16, and 6. 0, 17, 14, 16, and 6. 0, 17. Oh God, I can't remember that much. 0, 17, 14, 16, and 6, right? Ah, yes, I somehow remembered. 6, not 0. 6. Here is 14, not 1/4. Okay, next row. Least is 26. So 0, 12, 11, 19, 0, 12, 11, no, 0, 12, 11, 19, and 2. 0, 12, 11, 19, and 2. 0, 12, 11, 19, and 2. Okay, and last one, 26 again. So 0, 8, 0, 8, 18, 17, and 2. 0, 8, 18, 17, and 2. 0, 8, 18, 17, and 2. Okay, now, same thing I have to do column-wise, correct? Okay, first column is anyway all zeros. Actually, so maybe I can just copy this. Yeah. Let's copy this here, right? It's a bit bigger than that one anyhow. Okay, anyhow. All right, now next column. Saving some time, I suppose. So this becomes 7, 0, 10, 5, 1. 7, 0, 10, 5, and 1. Yeah? In the third column, this becomes 0, 12, 6, 3, and 10. 0, 12, 6, 3, and 10. this column is to 16. So 13031. 13031. Digital pen they haven't provided today. And again, calling them and getting them will take time. So I know, but what to do? They haven't provided today, so it's okay. It's just another 2 minutes. Then we're going back into Excel, so don't worry. Okay. So what was it? 13031, right? 13031. And last one already has a 0. So 10622. Okay, so now minimum number of lines. Remember, we need minimum number of lines to cover all the zeros. So one line is here anyway. Now you have, there are 2 zeros here, so we'll take this line also. And now we have 2 other zeros, so it's just 4 lines, and we need 5 actually. So which one should we take, row or column? It makes no difference really. Okay, I'll take rows here, okay? I'll take rows. Row here and row here, okay? So 1 becomes 1, okay? So, our next thing is, okay. So, let's do it over here. Okay, so remember one more reduction step. So 1 is the least uncovered element, so it has to be added at the intersections here. So 1, 1, 1, it will become 0, 0. Okay, 1, 1, 1, 0, 0. These remain unchanged. 1, right? So yeah, so in each, so second matrix, in each column, 7 or 8, where, which one? In the first row column, second column, 7. Second matrix, in the second column here, I subtract 7 to get this, right? And then you have to do each column separately, right? So here minimum is 7, here minimum is 8, here the minimum is 16, here the minimum is 0, like that. Okay? Alright, here however, we look at the uncovered element. Uncovered element minimum is 1, right? So first we add them at the intersections, 1, 1, 1. These remain unchanged. So this is what, 4, no, 7. 7, 0, 1, 1. 7, 0, 1, 1. And this is 0, 12. 0, 12, 2, 0. 10, 6, 0, 6, right? 10, 6, 0, 6. Okay, so these remain unchanged. And now we subtract 1 from each of these. 4, 2, 2, 1. 4, 2, 2, 1. And 0, 9, 0, 1. 0, 9, 0, 1. Okay, now where the zeros are the important thing. So do we have enough zeros? In other words, do we have 5 lines now? Let's see. Okay, so where are some common ones? We can take this one line that has 3. This one has 2. And then we see there are 3 of them in different things. So we have to have 5 different lines. 1, 2, 3, 5 different lines there. Yeah. Okay, yes. All right, see, basically, okay, I'll redo this also. See, basically, we look at where are all the zeros. So these are, these are all the zeros here. And we want to cover up all the zeros with a minimum number of lines. So how to do that with minimum number of lines? Well, look for rows or columns with maximum number of zeros, right? So which row or column has maximum number of zeros? This one, of course. So first row I'll take is this. This has maximum number of zeros. So let's get that over with. Okay, so one row is done. Now we have some other zeros, and these two come in the same row. So again, we'll take these two together. That makes another. And then now we have three zeros in totally different rows and columns. And so we'll need three separate lines for them. Either we can take three vertical lines or three horizontal lines. So the point is we need 5 lines. Everyone agrees? Okay. Because we need 5 lines, we can now do our allocation. So we can forget about these. So those lines were just to see how many lines. Now that we see that there are 5 lines, we can start with the allocation. Okay, so let's start with the first allocation. So any row with a single zero? Yes, this has a single zero here. So allocate this, and there are no other zeros to cancel here. In the second row, there are 2 zeros, so we can't do anything. Third row, there's a single zero, so allocate this. And because we allocated the third, assigned the third row there, how did we get the third matrix? First column as 1. So remember, we have to add this uncovered element at the intersections. So subtract from the uncovered elements, add at the intersection. That's why we got 1 there. That's why these 3 ones have come. They were 0, 0, 0, but because we have to add, we add 1, 1, 1 there. Okay? Okay, so here we assigned row 3 to column 4, and because of that, this 0 cannot be assigned any further. And so we can cancel this 0 out. As I said, it's not cancelling it, it means it's not being considered. We cannot assign there, that's all. Now, in the fourth row, there's a single 0, and again we can cancel this. And so we're left with only a single 0 here in the fifth row. Assign this, and now cancel this. And finally, we can assign this last 0 here. Okay, so what is our cost? Well, we have to go back to the original problem. So this, and this. So whatever this is, 38 plus 25 plus 39. Okay, I have a calculator. So 38 plus 25 plus 39, sorry. Okay, 38 plus 25 plus 39. And then what else? These two in the corner here. Plus 26 plus 34. Plus 26 plus 34 gives us 162. Okay, so our cost is 162. Okay, optimal total cost. All right, so it's just a matter of practice. Nothing to worry about. And don't worry, the problems, okay, I'm stating something about the exam. In an exam situation, problems won't be difficult. It will be simple. Okay, so nothing to worry about. Okay. Okay, but away from the, yes, there's one other type of problem that we should discuss, which is transshipment problem. I didn't deal with that yesterday, right? Transshipment? Did I talk about transshipment problems yesterday? So there's that bit of that chapter left over. How did we arrive in third matrix? Column, Column, This column, you mean? See, basically, when we're doing this reduction step, see, elements that are covered by one line only remain unchanged. So these 2 zeros remain as these 2 zeros here. Okay. Now, because these were covered these were at intersections of 2 lines, we have to add back whatever we subtracted here. For the uncovered elements, we subtracted 1, the least uncovered element. That same thing has to be added in the intersections. So 1, 1, 1 is what we get here. Okay? Administrator himself, huh? Let's see. Okay, just one small thing. Let's see who. No, administrator is ours only. Oh, no, administrator. Okay, anyhow, doesn't matter. Okay, if you want to call yourself an administrator, fine, that's okay. Anyway, so yes, yesterday we didn't speak about transshipment problems, and that is an important type of problem. So let's look for that particular slide again. Transportation and assignment problems. Okay, so quickly we'll finish that and then get to it's only 1:15. Okay, so we had transportation problems, assignment problems. Actually, transshipment problem is an extension of transportation problems. Okay, so in transshipment problems, well, basically, see, this is the beginning of supply chain. See, in a transportation problem, we had supply points, we had demand points. But in supply chain, directly, can we produce it and straight take it to the customer? No, obviously that's not what's done. So there's usually some take it to some warehouse, maybe mix it with some other products or put it with some other products, take it to different distribution centers, then from distribution centers to other, so even before distribution centers, there are super stockists and lots of layers are there. Okay, so basically a transshipment problem does that. It builds in layers between supply and demand points. Okay, so transshipment problems are transportation problems in which a shipment may move through intermediate nodes called transshipment nodes before reaching a particular destination. So this is how we design supply chains. We have supply points. We have to look for where are warehouses, where are distribution centers, where are retail outlets, and where are customers. All that way. Okay. So transshipment problems can be converted into larger transportation problems, but anyway, we'll just do it through Excel. That's the simplest. It can also be solved through general LPP, and the network representation, for example, is as follows. So what we have is, on the left side, we have sources, in this case, 2 supply points with fixed supply, and on the right side, destinations or demand points with fixed demand. And intermediate points are points like warehouses or true points, right? So we ship it to some other point through which it's then maybe combined with other things and carried to the destination. And so we have 2 sets of costs, CIJs from supply points to demand points, and then CIJs from supply points to transshipment points, and then from transshipment points to demand points. Notice in some cases we may be able to directly ship as well. So, but only if there is a direct arrow from supply point to demand point. Okay, we have to reintroduce those if there are. Okay, so what is the formulation? Just as before, the total cost is summation Cij into Xij, where Xij is the quantity shipped from supply point I to demand point J, where it could be supply point or intermediate point, depends on. Okay. Now, supply constraints are the same. Summation Xij less than or equal to Si for each supply point. Demand constraints are also the same. Summation Xij summed over I is equal to Dj for each demand point. This is assuming excess supply. And we have a new set of constraints, which is very straightforward, right? Think about it. What are these intermediate points? It's just a through point. So whatever comes into the intermediate point should go out. So the sum of units entering should be equal to the sum of units exiting. So for example, for point 5 here, x15 plus x25 should equal x56 plus x57. Right? That's expressed in this one here. So summation Ik summed over I minus summation Kj summed over J should be equal to 0. So what comes in must go out. okay, for each such transshipment point. So, shall we try a problem? There's a problem. Thomas Industries and Washburn Corporation supply 3 firms, Xerox, Hughes, and Rockright, with customized shelving for its offices. They both order shelving from the same 2 manufacturers, Arnold and Supershelf. Weekly demands for the users are 50 for Xerox, 60 for Hughes, and 40 for Rockright. Both Arnold and Supershelf can supply at most 75 units to customers. So let's look at demand and supply here. 50 plus 60 plus 40 is 150, and 75 times 2 is also 150. So it's balanced actually, so convenient for us. Okay, so additional data is as follows. So costs from Arnold and Supershelf to Thomas and Washburn are these 5874, and then from Thomas and Washburn to Xerox, Hughes, and Rockright are 158344. Let's see if I can. I think I have to come out and do this. Can I? Oh no. Okay, I think I'll just directly type it. So let's solve it directly from here. Okay, so what was it? Okay, Thomas, Washburn, Arnold, and Supershelf. Okay, all right. So Arnold, Supershelf, I'll call it SS. Thomas and Washburn. Okay, Thomas and Washburn. Okay, so these are the costs. What are the costs? 5874, right? 5874. 5, 8, 7, and 4. And what did we have? The supply, right? What is the supply? 75, 75. Yes? And then from Thomas and Washburn to Xerox, Hughes, and forgotten the last one. Oh, Rockright. Okay. All right. So this is this one. And what are the costs? 158344. 158344. Okay. And what is the demand? Okay, demand. So 50, 60, 40 or something, right? 50, 60, 40. Yes. 50, 60, and 40. Okay. So what we're going to do is very simple. We will take both of these as to create our variables. So we don't need supply here, and all of these become our variables. Okay. Now, supply constraints will come as row sums here. Demand constraints will come as column sums here. Right? And intermediary constraints. Okay, so, let's do it in a different way. All right. Okay, so what we'll do is we will list out all sets of constraints here. So supply constraints, Okay, supply constraints for these two. Okay, then there are demand constraints. Okay. Oh, it looks more better to write it like that. Okay, so this, this, okay, and then transshipment constraints. Shipment. Of transshipment constraints. Okay, and that's for these. Okay, so now supply constraints are that the total, the row totals here should be equal to the supply available there. So just copy this, or otherwise I'll just put this here. Okay, so equal to 75, 75. Then demand constraints are column sums. The column sums here should be equal to how much? This value here. This column sum. Okay, I'll just put the constraint part first. And this is equal to this. Okay, and what is this? This is equal to the second column sum here, and this is equal to the third column sum. Okay, now in that respect, okay, these constraints are equal to 0 because I'll take inflow minus outflow. Okay, so inflow here is the column sum here. Okay, outflow is the row sum here. Inflow is the column sum here. Outflow is the row sum. Okay, and we'll put our total cost over here. So sum product of, okay, so this with this, okay, plus again sum product of this with this. Okay. Okay, so both together. Okay, so for example, if we had 3 layers, again the costs of each layer will come as a separate thing, add up all the 3 layer costs, and again you'll have constraints for each. So this side constraint, so supply constraint, demand constraint, and each intermediate point. Actually, it's the intermediate point that connects the supply with demand in this case. Otherwise, there's no constraint connecting them. Okay, so we're minimizing the total cost. Now we have 2 sets of variables, so you have to be careful. This set of variables, comma, this set of variables. So just a simple comma will do to separate them. And constraints. What are the constraints? Well, these are supply constraints. I'll put equal to everywhere just to make it simpler. Right? These are equal to these. And these are equal to okay, there we are. All right, so what this tells us, so 75 units from Arnold to whatever Thai something, Thompson, and 75 units from Super Shelf to whatever Wow is. Now these 75 split as 50 to Xerox and 25 to Hughes, These 75, 35 to Hughes and 40 to Rockford. Okay, the total cost is 1150. Minimum total cost. Okay. Okay, very, very simple. Okay, I think one of the problems is similar to this. Okay, transshipment problems. Okay, so we've seen some interesting applications here. We have half an hour. I think I'll do this. Okay, so we'll do this multi-criteria in the next class. Okay, we'll just finish off this, what they're called, network problem, network model. Oh, wait, what happened with that? Okay, so let's see whether they got the same answer. Should be the same answer. Right, 75, 00, 75, 50, 25, 00, 35, and 40. So are they getting the same reduced costs? Yeah, 2400, 3300. Right. All right, so 75 split cells 50 and 25, 75 split cells 35 and 40. Right. Okay, and dual values. Oh, did I get negative dual values? That's an important thing. Okay, yes. Notice here, many of the dual values are negative. Okay, so for example, okay, transshipment constraints give us negative dual values, and demand constraint gives negative values. Huh? Oh. So if the demand increased at a particular, at rocks, actually we can reduce the cost. And even transshipment constraints, we can improve. Anyway, that's not there, but at least this one being negative is surprising. Usually supply points we have negative rocks. Which one is rock? Because the costs are much less here. Okay, so what will happen is, if the demand at rocks increases, then what will happen is, some units will be shifted to rocks from the others because it's more costly to supply those. And so the cost will decrease. We won't satisfy all the orders, but the cost will decrease because demand will be shifted from more costly centers to this. That's why that's becoming negative. Generally, supply points also, when we have higher supply, the cost decreases because the supply can be rerouted to a lower cost. Whichever has lower cost, we'll reroute and get. Okay, so generally, supply constraints should have negative dual values. I don't know why this is positive. Okay, so that's the end of the chapter. Okay. Now, let's quickly, in whatever time we have left, talk about various network models. Okay. Of course, what we had seen was some examples of network models. So, transportation as well as assignment problems are examples of network models. These are slightly different types of networks. One is called the shortest route problem. Another is called the minimum spanning tree problem. And another is called the maximum flow problem. The shortest route problem is, for example, suppose I want to go from here, to some other point. And I have various intermediate points and different paths that I can take. I want to find the shortest path from here to my destination. Right? Amongst the given routes, what is the shortest path or least cost? Actually, those who have studied a little project management will know of a related problem called PERT CPM. In CPM, we're looking for the longest path. Actually, if we can get the shortest path, we can get the longest path. The technique is very similar. Okay? So, we'll talk about that first. Then we'll talk about spanning tree. Okay? So, in a network, suppose, for example, you're in a connected network. And suppose, for example, some failure occurs between telecommunications and some emergency is there, you need to contact people. The minimum spanning tree is a network that connects the people at minimum minimum weightage type thing. So, for example, in terms of minimum cost or something like that, then you can find a way of connecting the people through the minimum cost type of. And maximum flow is something that we all face. Of course, traffic is there, right? And why does traffic occur? Well, because certain routes have lower capacity. Right? There's some narrow roads, and everyone has bigger and bigger cars. Of course, some point some problem will occur. Right? So maximum flow looks at, of course, a much simpler version of that. We can't solve Bangalore traffic problems overnight, but anyhow, this perhaps can give an idea of how to solve it. So in maximum flow problem, you have a network of maybe pipes or roads or whatever, and you want to send units from a source to a destination. You want to see what's the maximum number of units you can send along the network from source to destination. Of course, it's much more complicated than that, Bangalore traffic, but anyhow, at least you feel that, yes, maybe we can solve it. Okay? All right, anyway, let's see. Okay, now the shortest route problem is perhaps the simplest of all to understand. It's concerned with finding the shortest path in the network from one node or a set of nodes to another node or set of nodes. So how to reach from these points to those points. If all arcs in the network have non-negative values, then we're going to use something called the labeling algorithm. So the algorithm we use is called Dijkstra's algorithm. Anyone has heard of Dijkstra's algorithm? Actually, since we mentioned this name, in my opinion, actually this Hungarian assignment method was also developed by Dijkstra, but he never published it. But I feel that he's also done that. He's a big Hungarian mathematician. Okay. Anyway, so the criterion to be minimized in the shortest route problem is not limited to distance. We can look at time, cost, whatever, right? So all this Google map thing tries to minimize your time. Again, if you have some cost things, then you can minimize cost and so on. Okay, so now the way we solve this is using labels, and closed brackets like this represent permanent label, and open brackets like this represent temporary labels. So there are permanent labels and temporary labels. Okay, so we start with the first node, initial node, and we label it as 0, S. 0 means the distance is 0, S means we're starting. Okay, so now the first number is the distance from node 1, which is 0. The second number is preceding node, this is the starting node, so nothing. For every other node, we'll have some other starting point and some other distance. So now for every point that we can reach from node 1, we give a distance and a node label that can be directly reached from node 1. So D is the distance from node 1, and N is 1 in this case, the preceding node. And every time, okay, so then amongst all the temporary labels, we look at the one with minimum distance, and we make that into a permanent node. Okay, so identify the tentatively labeled node with smallest distance and make it permanently labeled, but put it in closed brackets like this. And then anything reachable from there, we update. So if the distance from this new node is less than what the earlier distance was, we update it. If it's more, then we don't need to update. Okay, and we continue until we get to the last node. And so arc distance from node K to node I plus the distance at node K. That's how we keep on updating. Anyway, when we solve it, you'll see. Okay, and blah, blah, blah. Oh, I've already solved it. Okay. All right, maybe I'll just rub out everything. Okay? Already solved it, huh? For interruption. Am I allowed to rub out things now? I can't, huh? No eraser. Maybe if I put something, then I'll get an eraser. Eraser. Only the ones that I've done now, huh? Okay. Okay, then we'll just follow instead of doing it, we'll follow the method. Okay, so we're starting with this network. Ignore all those yellow things. Okay, so we have this network 1, 2, 3, 4, like this. 1, 2, 3, 4, 5, 6, 7, and these are the distances 4 and so on. I think we change this to 2 later, but anyhow. Okay. Oh. Okay. All right. So to start with, so we label 0, S here. Okay. So the first step, we put 0, S. 0, S, and then we get temporary labels of 4, 1, 7, 1, and 5, 1. Okay. So temporary labels we'll get are 4, 1, 7, 1, and 5, 1. Yes. Okay, now amongst these, which one is least? 4, 1. So this node 2 becomes 4, 1. Okay, so node 2 now becomes 4, 1. And what will happen now? Huh? Those are distances, distance or cost or whatever. Okay. Now, once I make this permanent, now this becomes reachable. So this becomes 4 plus 5, 9, 2. And this now becomes how much? 4 plus 3, 7. 4 plus 3, 7, 2. Right? Oh, acha. So that's perhaps why I changed that to make it 5, so that it becomes shorter. Okay. Anyway, we will follow the original one. Okay, so this becomes 4, 1, 7, 1, 5, 1. Okay, so this is the tentative. This becomes permanent now. Okay, so 4, 1 becomes permanent. This becomes 4, 1. And so now everything reachable. So this becomes 9, 2, and this becomes 7, 2. But since the distance is not improving, it will remain the same. Okay, so 7, 1, 9, 2. If the distance had decreased, then we would have done something there. Now, which is the least? Now, this one, right? So this becomes permanent 5, 1. Okay, permanently 5, 1. Right? And now what is reachable from here? So from here, this now becomes reachable, right? So 5 plus 1 becomes 6, 4. And this becomes 13, 4. Right? So 6, 4, 13, 4. So earlier it was 7, 1. Because this distance is less, we've updated it. When the distance is more, we don't update. Okay? All right. So since the distance is less, we've updated, and 13, 4 there. Now, which is the least of them? This one is least. So we update this, and now what will happen? So 6, 4 becomes that. And now what will happen? 6 plus 2 is 8. So this will update as 8, 3. See, this has become permanent. Now this is reachable. 6 plus 2 is 8, which is less than 9. So this will update. This will become 8, 3. And 6 plus 6 is also 12. 12 is, so this will become 12, 3. So that becomes 8, 3. This becomes 12, 3. Okay? So 8, 3, 12, 3. Now, which is the least out of these? 8, 3. So that becomes permanent. Okay? That becomes permanent. And now we can read 7. So label at 7 becomes 14, 5. Okay? 14, 5. And 8 plus 3 is 11 also, right? It was 12. 8 plus 3 is 11. So this becomes 11, 5 at 6. Then this becomes permanent. Okay, 11, 5 becomes permanent. When that becomes permanent, 11 plus 2 is 14, so that also updates. So it becomes 13, 6. 13, 6. And finally, that is made permanent. And so that becomes our final thing. So the final thing is with this becoming permanent. And now we can get shortest distance to every point. So shortest distance from 1 to 2 is 4. Shortest distance from 1 to 3 is 6. From 1 to 4 is 5. Okay? And that tells us the shortest path also. 4, 6, 5, and shortest path is 1, 2, 1, 4, 3, and 1, 4. Okay? Yeah, 1, 4, 3. Then shortest distance to 5 is 8, and the path is 1, 3, 5. Shortest distance to 6 is 11, and the path is 1, 3, 5, 6. And shortest distance to 7 is 13, and the path is 1, 3, 5, 6, 7. Okay, so that comes like this. So we get the shortest distance from every other point, from the origin to every other point, as well as the shortest path from the origin to every other point. Okay, very nice thing. Okay, so this is called Dijkstra's algorithm. Now, later on, we will see, okay, otherwise, shall we solve this by linear programming also? Shall we solve by linear programming? Okay. So, how do we solve by linear? So, do you think that we can solve by linear programming? What do you think, and why do you think that it can be solved by linear programming? Okay, so let's go back here. Something happened here, right? Oh, the chat. How did we assign 4, 1? I didn't get it. Huh? In the beginning, huh? No, okay. See, in the beginning, 4, 1 is like this. Okay, so let's go to that. All right, see. Basically, the moment this is labeled 0s, anything we reach from here, we just look at, so add the current distance to the distance on the arc. So 0 plus 4 is 4, and the preceding node to this is 1. Here 0 plus 7 is 7, preceding node 1. Here 0 plus 5 is 5, preceding node is 1. And then when we update, if it decreases, then we take the preceding node from there and whatever the new current distance is. Okay, so for example, here, right, when we made this, when we made this permanent, when we made 5, 1 permanent, 5, 1 became, 4, 1 became permanent now. Now that 5, 1 becomes permanent, 5 plus, see, earlier it was 7, 1. That is direct from 1 to 3, right? But now when this becomes 5, 1, 5 plus 1 becomes 6, which is less than that. We update it with the new shorter distance, which is 5 plus 1, 6. And which one is the preceding node? To get this 6, we have to come from 4. And that's why that changes each time. Okay. Okay, anyway, we'll later on see there's a better way. Oh, sorry, we were doing the linear programming method. Okay, now in the linear programming method, the concept is very simple, right? Okay, linear programming method actually works best if we have, I see. Okay, all right. So let's assume, okay, we'll have to make an assumption here. What is the assumption? We'll have to have directional. So we'll have to have directional thing. Undirectional, there's a problem. Okay, so in other words, I'm saying that I'll be taking arrows conveniently. So from 1 to 2, 1 to 3, 1 to 4, then 2 to 3, 2 to 5. Generally, we don't take arrows, but I'll take arrow from 4 to 1. Okay, 4 to 1, 4 to 6, then 3 to 5, 3 to 6, 5 to 7, 5 to 6, and then 6 to 7. So these are the various arrows I'm taking. Okay, so each of those becomes a variable now. And this is an example of binary programming. Okay, so where's the picture? Okay, I think I'll use this picture because that picture is a bit, okay, so my arrows are therefore, not this. This is a simpler problem to solve. Anyway, Okay, so what is this one? So x12, 13, 14. Okay, so x12, x13, x14. Okay, then I'm taking 2325, x23, x25, then okay, I'm taking 4346. I'm not, actually they should have labeled this as 3 and that is 4. Right? Because 43 doesn't, anyway, doesn't matter. X4346, X43, X46, then X35, X36, X35, X36, then, oh, sorry, X35, X36, then X5657, X56, X57, oh, what happened? X56, X5, and X67. Okay, so actually this nomenclature, I think, maybe they forgot or maybe they overlooked it. This should have been a 3, that should have been a 4. Then it looks better. Anyhow, it doesn't matter. All right, now the costs we're going to put in now. So 475, the objective will be costs. So objective function, these are the variables. And the objective function is minimize the total cost. So total cost is 475. 475. Then 35. I'm doing it in the same order that I've chosen. 35. Then 4346. Okay. 18. 18. Okay. Then 3536. 26. 26, and then 36, 362, 3, 6, and then 2. Okay. All right. Now, how should we go about this? Well, basically, I have to choose a path. So I have to select some of the arrows. Yes or no? So I'll put x equals 1 if it's selected, 0 if it's not selected. Yes? And the point is, I have to choose one of the arcs from 1 and one of the arcs has to enter 7. At every other point, whatever we come, if we come, then we have to go. If we don't come, then we can't go. Right? And so, entering must be equal to exiting. The sum of entering arrows must be equal to the sum of the exiting arrows. Very basically that. Yes? Okay, so each node will have a constraint. So node 1 to node 7. Each node will have a constraint. So in node 1, one of these has to be equal to 1. So 1 plus 1. So x12 plus x13 plus x14 equals 1. Then, if we look at what is entering node 2, x12 is entering node 2, and what is leaving? 2, 3, and 2, 5. So minus x12 plus x23 plus x25 equals 0. Yes? So minus x12 here, and plus this plus that equals 0. Then for x4, so node 3, minus x13 minus x43 and plus x35 plus x36. In node 4, minus x14 plus x43 plus x46. Node 5, we have minus x35 plus x56 plus x. There are 2, 5 is also there, sorry. 2, 5 and 3, 5, 5, 6 and 5, 7. Node 6 is here. So minus this plus this, oh, minus this, sorry. Minus this, and plus this. Okay? And node 7 is 5, 6, and 5, 6. Okay, so what are the constraints? Well, it's very simple. Oh, what am I doing? Sum product. Okay, coefficient, variables and coefficient. Okay, and fix the variables. Okay, so copy this on the left hand side here. Okay, and all constraints are equality constraints. Now, all the intermediate points are 0. What comes in comes out. And the origin point and the destination point must be 1. So we must leave the origin and we must enter into the destination. So one of them must be 1. Okay? All the other points have to be 0. Right? Very simple, no? Okay, so now let's see what happens. So we're minimizing the total cost. Here are all the variables, and the constraints are all equal to this column here. Yeah? Okay. This sensitivity, you know, though it's binary, I didn't put in binary. I thought, let's see what happens. So, x, so 1 to 4, 4 to 3, 3 to 5, 5 to 6, 6 to 7. Is that what they got? And the distance is 30. That's what they got? I think so. Okay. Yeah, 13, 1, 4, 3, 5, 6, 7. Right? Very, very simple. Okay? All right, good. So, really simple problem that was. Now, spanning tree problem. Okay. This is another very simple problem actually. It's hardly, okay, what is the problem? Can we have a chart of this simplex? What? Chart means? Chart of this simplex expression. Actually, Vivek, I didn't understand the question. Sir, can we have a chart of this simplex expression? Means a diagram in that, that's true. Yeah. So, we've already solved the problem. That's why we didn't, yeah. So, in Excel, yeah, you, you can, there are trees, yeah, there are some drawing tools, but I'm sure you people being young can do it much better than me. I'm an old timer. I don't think we can. That's it. It's a very good question. I've seen it done. So there are tools for doing this. What do we have? In Word, you have those hierarchy things and so on, right? Networks. In Word, you have such. Okay, wait 1 second. In Word, it's there. In Excel, it will be there or not. Insert will have something like that actually. Chart, but diagram, illustrations, smart art. It's art. See, for graphs, for graph theory, so there's a separate subject called graph theory, and there are separate software for doing that. I haven't seen it done in Excel as such. You have some diagrams that are similar, but they're not as good as yeah, so my answer isn't really the best answer to this. I'm sure there are certain graph theory add-ins that you can use that do better. But yeah, I'm sorry. Okay, give me some time. Maybe if I find something nice, I'll report it, and let's see. But these you can use something like this. This is not the best picture in the world. No. Okay, let me see. But these types of things are there. These types of things, but no, obviously this is not as good as. Okay, okay, some type of linkage systems like this is cycles. Actually, sometimes when we draw, for example, influence diagrams and so on, there aren't good enough tools in Word as well. See, for example, you want to draw, for example, okay, see something like this, for example. Suppose you want to extend it with something outside the cycle. It can be done. That's a problem actually. So, okay, anyway, we'll see. Okay. Anyway, before we break, let's just quickly also talk about this last thing because it's very easy. A minimum spanning tree. Okay, so minimum spanning tree is what we talk about. Okay, so if you remember, okay, so let's talk about. So a tree basically is a set of connected arcs that does not form a cycle. It's an connected acyclic graph. A tree is a connected acyclic graph. So it's connected. That means every point, every node is connected to every other node, but it has no cycles. Okay? A spanning tree is a tree that connects all nodes of a network. So we have a network. A spanning tree is a sub-graph, a sub-tree of that network that connects all the nodes. And the minimum spanning tree problem seeks to determine the minimum sum of arc lengths necessary to connect all nodes in the network. So we want to maintain connectivity at minimum total cost. The criterion to be minimized in a minimum spanning tree is not limited to distance, even though closest is the word used. We could have time, cost, and other things. Okay. All right. So, and it's very simple. I think this is called Kruskal's algorithm. So arbitrarily begin at any node and connect it to the closest node. So start at a node and connect to the closest node. The two nodes are referred to as the connected nodes, and remaining nodes are unconnected. Then identify the unconnected node that is closest to one of the connected nodes. And again, if they're two equal values, choose any one of them. Add this new node to the set of connected nodes. Repeat until all nodes are connected. So just choose things that are closer. It's like a greedy algorithm. Okay, so right, this is a greedy algorithm. So suppose we've already done this, but okay. So start anywhere. So where do you want to start? Okay, start with the shortest. I think that's the easiest thing to start with. Either 3, 6 or 7, 10. Right? Where do you want to start? Okay, let's just follow what they're doing. Okay, so connected nodes are 1 and 2 they've taken. Okay, 1 and 2 are these two here. Okay, so these we've connected, and the length here is 30. Okay, all the other nodes are unconnected. Okay, 3, 4, 5, 6, 7, 8, 9, 10 are unconnected. Now, what do? We look at what is closest to this. So on this side is 45, on this side is 25, 35, and 50. What is closest? 25. So bring 5 into the connected set. Okay, so closest one is 5 at distance 25 from node 2. So bring that in. All the others are still unconnected. Okay, now that 5 is included here, what is the closest to that? Next one is 7. Which is at distance 15. Okay, so next one is 7 at distance 15, and so that's included. Now that 7 is included, what do we have now? So forget all those. We have 20, 30, 20, 30. So 20 is the shortest. So bring in 10. Okay, so 20 is the shortest, bring in 10. Okay, after that, Okay, we have 35, 25, 30 and all those. So next comes 25 here. Okay. Okay, 25. So bring in 8. Okay. Then, so these are all connected here. So now these are already within the network. So our network is this so far. Next distances are 35, 40, 40, 45. So what is the shortest? 35. So connect 6. Now that all that is there, now what are the distances? So 20, 45 and all that, right? So next we choose 20, then 30 and finally 45. Okay, so next will be 6, then 3, then 9, then 4. Okay, so very, very simple this is. So after 10, 8, 6, 3, 9 and 4. Okay. So very, very simple. Kruskal's algorithm. 2 branches from 10. Yeah, because see, now that we have this branch, all of these are covered. We don't need to consider that already. So just look at the remaining part of the network. See, these are covered. We don't need these anymore. 10? Yeah, these are already connected. Only the ones which are not connected, those have to be considered. Okay? At any point of time, just look at the ones that are not connected to the ones that are connected. Within the connected one, there is no need because it's already connected. Okay? Very, very simple algorithm this is. Okay, so this is our final minimum spanning tree. 1, 2, 5, 7, 10, then 8, 10, 8, 6, 9, 3, and 4. So connected acyclic. Okay, maximum flow problem. At least let's describe it quickly. Well, there are 2 ways of solving this one. Okay, so suppose we have a model like this. So this time, what we want is, we want to find maximum flow from the source, the sink, and the numbers represent capacities. In each route, what is the maximum amount that can flow? Okay, the maximum amount that can flow. Okay. So, is concerned with determine the maximum flow. Okay, maximum flow at arc with arc capacities. Okay, so basically, what this is an example of a capacitated transshipment model. Okay, capacitated transshipment. So whatever we studied about transshipment problem, the same thing will actually be applied here in a sense. Okay, so what do? What we do is we connect this sink back to the source. So we have flowing amount. The whole flow we connect back to this, making it into a conservative system. And now what will happen is at every node what comes in will go out. So the whole flow is conservative now. Okay? And it's the same thing. So whatever this flow Z is coming in, Z equals x11, x12 plus x14 plus x13. And then at each node, what comes in must go out. So all the entering arrows must be equal to all the exiting arrows, sum of the entering arrows. And in that way, you're maximizing Z subject to those constraints and subject to capacity constraints. x12 is less than 4, less than equal to 4. x14 is less than equal to 4, and so on. So as a linear programming problem, very simple to build. Okay, so all right, so maximum flow, that is xk1, that is the Z, and at each intermediary node, xij summed over I minus xji summed over j must be equal to 0. So what comes in must go out. Okay, and each xij is less than equal to cij, the capacity, and so on. Right? So, okay, all right. So shall I do it quickly? Okay. All right. So it's okay. This is the problem, and let's quickly model it and finish it. May as well just why keep it hanging till the end? What was this? Was a different one. Okay. All right, so what variables do we have? Can I copy this? Oh no, I can't. Maybe I can copy this. Okay, let's see if I can copy it. Okay, that didn't work. Okay, anyway. All right, so I'm calling this as Z and the others as Xij. Okay? So X12, we have X12, X13, X14. Okay, and we have reverse flows also. That's another problem. I don't like this reverse flowing thing. X12, X13, X14. Sorry. Next class, huh? Yeah, I'm hungry also actually. Okay, or otherwise, anyway, it's all uploaded. Can you all try it and come? Why should I do everything? Right? Try it and come. Okay, this is a good idea. All right. Oh, we have to save this. Okay, so let's delete this one. And this is network, transportation, assignment, and network. So save as, sorry? Yeah, I'll put it here. Descriptive analytics, transportation, assignment, and network models. Oh, transshipment also. One second. Sorry? Transshipment. Okay. Prescriptive analytics. Yeah. I'll remind them also. Yeah. Has it been uploaded? No, huh? Okay. We'll just tell them now. We'll go downstairs and tell. What should we call this? Hungarian assignment method 2 or something. EG2. Whatever. Okay. Okay, so everything is there. Yeah, in fact, I also have to tell them about, yeah, okay, so my other class also, in fact, that also has to be uploaded. Okay, so we'll meet again probably next week.